Okay, on today's review, just using this platform to kind of remind us of the topic of accumulation, and very generically speaking, when we're talking accumulation, we looked at this most recently as finding a total number using an integral given a rate of change, something like if we want to know how many miles have been driven, that our miles end up being the integral of some interval of our miles per hour function, very generically speaking. And so I want you kind of running everything through that frame of reference, is that we're talking about using integrals to help us with our accumulation topic here. So on this first one, a free response question that was given, that was in the calculator part, says there's no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate modeled by f of t equals 7t e to the cosine t cubic feet per hour, where t is measured in hours since midnight. Janet starts removing snow at 6 a.m., or time equals 6, and our rate in cubic feet per hour in which Janet is removing the snow from the driveway is shown in the piecewise function. G of t is 0 from 0 to 6, 125 from 6 to 7, and 108 from 7 to 9. So, kind of keeping all that in mind as we are going through this problem. First question, how many cubic feet of snow have accumulated? So the accumulation part of it, snow is accumulating here, which would be this function right here, f of t. How many cubic feet of snow have accumulated on the driveway by 6 a.m.? That would be our rate is in cubic feet per hour of f of t. So we would be looking at the integral from 0 to 6 a.m. of our accumulation rate, which would be 7t e to the cosine t dt. And I just went to my calculator and I typed that into my Math 9 and got 142.275, and that would be in feet cubed, or cubic feet, just accumulating from 0 to 6. Next, find the rate of change of the volume of snow on the driveway at 8 a.m. So if we're talking rate of change, what we would be looking at here is, let's say we allowed our total amount of snow to be the function s of t. So that would be the combination of how much is accumulating, f of t, minus how much is being removed, g of t. And this is specifically at 8 a.m. and the total amount of snow would be that integral. And so if I want to know then the rate of change of something, the rate of change of the volume of snow is going to be its derivative. So the derivative of our amount of snow, now the derivative of an integral is just the function inside, so that would be f of t minus g of t, and we are supposed to be doing this at 8 a.m. So going up to our function here, I went ahead and plugged 8 into each of those functions. E to the cosine of 8 minus, and then g of 8 would be 108. And we find out that we have a rate of negative 59.583 feet cubed, cubic feet per hour, I should say here, rate of change. Okay, and then this next one's a little bit hard to wrap our mind around here, but it says, let h of t represent the total amount of snow she has removed. And so when the rate of the removal is g of t, Very generically speaking, h of t would then be the integral of g of t, but the problem is it's a little bit different as you look at each of the different parts because of the piecewise nature of g of t. So if we explore each of those individual pieces, first of all, let's look at that first piece that says that g of t goes from 0 to 6. Okay, well, if g of t is 0, then h of t from 0 to time equals 0 to time equals 6 is also going to be 0. The integral of 0 is just 0, right? And so then let's look at our next one here that goes from 6 to 7, and that's going to be that h of t. Now, first of all, from 6 to 7, remember, h of t is the total amount we have accumulated. During the first 6 hours, we accumulated nothing, and then we add to that how much we accumulate between 6 and whatever time it is up to 7. Okay, and that's happening at a rate of 125 cubic feet per hour. So let's explore this part of it real quick. Remember that if we are looking at a constant function, that's the same thing as the constant times the difference in your interval, which would be t minus 6. And since we're adding that to 0, that really does become h of t for the time from 6 to 7. Okay, and then our last part is from 7 until 9. So h of t is going to equal, and if we look at our time that we would start this at would be time equals 7, and so we would be adding whatever we add from 7 to 9 to whatever we already have at time equals 7. So at h of 7, whatever that is, what's that we ended up with at the end of that last interval, and we'd add to that what we get from 7 to whatever time it is in that range from 7 to 9. And our function again is going to be a constant, so we'd have 108 dt, and again as you look at that, that's going to be 108 times t minus 7. So putting that all together, I'm going to have to erase some of this because I kind of ran out of room here, so hopefully you've got that kind of down here. So summing all that up, we can again write h of t as a piecewise function, gathering what we just talked about, is that in that first interval that goes from 0 to 6, we're not going to remove anything because she doesn't start removing until 6 a.m. So from time equals 0 up to time equals 6, we remove a total of nothing. From time equals 6 to time equals 7, our removal is going to be nothing plus whatever 125 times t minus 6 is. Again, from what we talked about in that how do you evaluate a integral of a constant discussion we just had. And then in our last one, okay, so let's say we do that for an hour. The most we would get rid of is 125. That would be what it would be at h of 7. 7 minus 6 is 1 times 125. Plus the 108 times t minus 7, again, comes from evaluating the integral of a constant, and that's going to happen from time equals 7 to time equals 9. That would be our h of t function showing how much we have removed. And our last question on this one, how many cubic feet of snow are on the driveway at 9 a.m.? Well, the cubic feet of snow on the driveway at 9 a.m. is going to be the combination of how much has been added and then also subtracting how much has been removed. So if we go back up above, the rate of what we are adding is f of t, which means the actual amount that we are adding is the integral of f of t dt, and we're going to subtract from that how much we are removing. Well, in this problem up here, we just found a function of how much we are removing, which would be h of t. So, kind of making this more specific, it says specifically at 9 a.m. So let's go ahead and write this out specifically at 9 a.m. So from time equals 0 to time equals 9 a.m. of f of t, and f of t, you can either put f of t because that's what it is named above, or actually go back up and get that function, which was what, 7 t e to the cosine t dt. And we're going to subtract from it whatever h of 9 is, which again, h represents how much has been removed up to that time. And h of 9 we can consult up here. H of 9 being 125 plus 108 times 9 minus 7. And typing all of that into my calculator, we find that we have removed, or not removed, we have a total of, added and also removed, landing us at a total of 26.335 cubic feet of snow. All right, moving on to our next one. In our next one, what we're looking at is the number of bacteria in a culture is grown at a rate, so they're giving us a rate of 33,000 e to the 2t over 5 per unit of time. And at time equals 0, the number of bacteria was 7,500. Find the number present at time equals 5. And a couple different ways we can go about attacking this, but basically they're saying at time equals 0. So at the very start of this, we've got 7,500 bacteria. Plus, and then we will accumulate bacteria from time equals 0 to time equals 5 at a rate of 3,000 e to the 2t over 5 dt. And so we would look at kind of cleaning this up here. Let's clean this up. So 7,500, and guys, I'm going to slide that 3,000 out front to simplify my integral here. Okay. And so let's say we didn't have a calculator on this one and using our integration techniques. I'm not really sure because it would be a chain rule to do the e to the 2t over 5. So I'm going to simplify that a little bit and do a little u substitution here. I'm going to let u equal that exponent, which means du would equal 2/5 or du over 5/2 equals dt. Oops. All right. Oops, not over 5/2. Over 2/5 or 5/2 times du equals dt. Okay, so coming back over here, doing that substitution, first of all, again, I can slide this 5/2 out front. E to the u du, so again, just doing my u substitution here, makes my substitution, or makes my integration process easier here. So the antiderivative of e to the u is e to the u. And I want to replace u with the 2t over 5. I'm going to clean this up here also. 3,000 divided by 2 is 1,500 times 5 is actually 7,500. Replace this u with what it originally stood for. That would be e to the 2/5 t. And we're going to evaluate that from 0 to 5. So evaluating that at 5 and evaluating that at 0. Okay, well 2/5 times 5 is 2, so on that first one we'd have e squared. 2/5 times 0 is 0, e to the 0 is 1. And distributing through, that's 7,500. Now 7,500 minus 7,500 would be gone, and we can see that our answer is going to be 7,500 E squared. All right. Moving on to our next one. This one is just representing using an integral, and they're asking you which one has been written correctly. R is the rate that the water is leaking out of the tank, and it's measured in, and time is measured in hours. Which of the following expressions represents the total amount of water that leaks out in the first 3 hours? So total amount of water is going to come from, if R is our rate, and time done in time, we would be looking at the integral of that, totaling up how much is under that rate of change, or that to get our total amount of water. And they said in the first 3 hours, so we'd be looking from 0 to 3. All right. On our next one, doing like a visual representation of our rate of change, it says the flow of oil in barrels per hour. So we're looking at a graph here of barrels per hour through the pipeline on July 9th is given by the above graph. So we are looking at the rate of change graph, or the velocity graph, if you will, in barrels per hour. Of the following, which best approximates the total number of barrels, which would be the area under the curve. Now, notice it does say approximates. We're going to be estimating here. We don't really have a function to work with. And so area under the curve is going to come from our best estimate here, approximate here. And if I were to convert this into shapes that I know, area under a curve, now our curve is going here, but that's not a shape I know. So if I were to make that into shapes I know, first of all, I kind of see a rectangle looking thing here. So I could say that's one of them, and a rectangle is going to be base times height. 24, your height's over here, 100. And then what shape are we seeing next to that, or above that? Best I can get here would be more like a triangle, kind of follows along those lines, and a triangle's area being 1/2. Base from 6 to 18 would be 12. Height would be here, from 100 up to 200 would be a height of 100. So then cleaning all this up to get an actual answer, 1/2 times 12 is 6, times 100 would be 600, plus 2,400, we'd be looking at 3,000 barrels. And our last one, just kind of reviewing different ways of talking accumulation. The velocity of a particle moving along a line at time t is given by the velocity 3t to the 1/2 plus 5t to the that's a 3/2 meters per second. How many meters did the particle travel from time equals 0 to time equals 4? So again, if we're going from meters per second to an answer in meters, we would do the integral, because we only want the top of the labels there. So we'd be looking at the integral from 0 to 4, totaling up distance, given a rate of 3t squared, t to the 1/2 plus 5t to the 3/2 dt. All right, so looking at this, we're going to go ahead and pretend that this one is a no calculator. So let's talk through our antiderivatives here. 3t to the 1/2 would have come from a t to the 3/2. Add 1 to that exponent. 3/2 times something gives me 3. So that something would be a 2. 2 times 3/2 is 3. 5t to the 3/2 would have come from again, add 1 to that. 3/2 plus 1 is 5/2. 5 times something gives 5/2 times something gives me 5. Well, that something would be a 2, and we're going to evaluate that from 0 to 4. So 2 times 4 to the 3/2 plus 2 times 4 to the 5/2 minus, and I'm going to show it, but plugging in 0 here is going to result in 0. Okay. All right, so coming back over here, cleaning up 4 to the 3 halves, 4 cubed. Let's see, 64. Square root of 64 is 8 times 2 is 16. And then on this next one, I kind of did it backwards. The square root of 4 is 2 to the 5th is 32. Times 2 is 64. And 16 plus 64 is 80. So it looks like we've moved a distance of 80 meters. All right, from here, your job is to try the accumulation worksheet, and we will discuss at our next Zoom meeting.